on this project, although I really would if I had like a bunch of free time, which I have none of right now. Hazel, you want to grab from the stool over there, on the stool.
Maybe when we don't
But
go to school.
there's this really cool kind of like, I don't want to say like trend, but there's this like do-it-yourself hack, if you will, of instead of buying flooring, you turn other stuff into flooring. So kind of this hipster mentality of like, how can we reuse stuff? So you make cool designs, and all of these are all pennies. So you get some brand new pennies, some older pennies, some really old pennies that are super dirty, maybe like rusted or patinaed. Maybe you intersperse the pattern so it's all just random. Maybe we actually really particularly make a pattern.
No. The one on the right there doesn't actually look quite random. It almost looks like it's trying to be a hexagon.
Yeah, kind of. Or this, a lot of new pennies there. A lot of really shiny ones. So,
I mean, they don't just have pennies, they have glazed over.
yeah, like polyurethane or something. Agreed. They got to do something. So, we have some pennies, right? And while we could start to kind of see, you know, how many can I... That's not the most efficient method. Now, what I have decided about my project is I want it to be based around circles. Because a penny is a circle. And, you know, circles are circles, so why not? So we're going to start to fill circles with pennies. So you, no surprise here, want to, from student.desmos.com, type in this code. Oh, there's a ton more here. I'll open this cart. We just want you emptying one cart before you do another. What do you mean?
Because the actual materials are worth more.
Oh, we're not buying the materials. We could just go to the bank and like buy a roll of pennies, right?
I guess.
So, I mean, if we're talking about what it would cost the U.S. government, then sure. But we don't really care. No. On slide 1, I do not want you trying to be perfect. It is an approximation. Sorry, I turned this off earlier for Mr. Flynn to play with this. All right, you are paced to slide 5. When you get there, you're going to be stopped. And then we'll talk.
Why?
Oh, come on. We've done Desmos before. What do you mean, why? We'll talk about the math.
Yeah, but why is picture all the same point?
Yeah.
Oh, what was the homework for yesterday? Is this you doing
There wasn't anything. We finished the master.
Cool, we might do that.
No, this is Dan Meyer, a math teacher that I look up to. Mr. Henry, I got you a Chromebook here, dude. You want a Desmos activity? So if you want desk, you can sit right here by Hazel, or back by Charlie, or by Audrey. You can sit back standing desk. A buffering machine. Go fix the internet. It's all you.
Oh, it actually worked. Not working. So what does today stand for?
Not until slide 5.
I'm having buffering issues.
It might just be because we're all trying to access the same thing at the same time. I mean, this is that whole block 3 like curse, right? When we all get back on Chromebooks all over the school. You might want to close out your browser and try it again. I like how gravity works in Desmos.
What's our catch?
Just keep going. Remember, in Desmos, you can go back and forth. So if you decide you want to go back to a previous slide, you can. Try different. I mean, I got another Chromebook. Maybe that finishes. I think everybody else is in there. The answer's not on my face.
Or is it?
Oh, that's not even fair. If we all had touch screens, this would be so much easier. A few of you guys have touch screens, and that's just not even fair. It's so much easier.
Why?
Okay, maybe fair is a little more.
Yeah, you just what do you mean?
Like, because then you can just drag, you know.
I mean, it's quicker, but you learn less.
You learn less? I don't know about that. Sorry, we don't need to be perfect. We just want the best we can.
The best I can do is
Okay, maybe I should rephrase this. We want close to great. Better than good.
Okay, I'll try.
That's. I mean, you could maybe get one more in there. But I mean, come on, that's pretty close to that.
Or just drag as many as you can, and then it'll just all work itself out. Okay, well, most of them eventually load in.
You can make that smaller. Interesting. You can even make it the size of one penny.
It's a bit bigger. It's a bit bigger. One lonely penny.
Guess. You're not calculating, you're making a guess. Because you don't have information to calculate. You don't know the radius, you don't know anything. All you know is this circle is about as wide as like the bottom half of his leg probably is, or if he laid his arm out, the circle probably that. So guess if you had a circle, and he's probably in the beach area. Because that's Dan Meyer. I have seen him speak about math many, many times. Like he's a great, great math teacher. Renee Descartes. That's you. Oh, you're actually really famous. I can't remember exactly what. Yeah, you can always Google these people. Guys, always, if you reach the stop screen of your Desmos activity and you're curious to find something else out, Google your anonymized name. That's a famous mathematician, right? And you can figure out what they did that they made a big enough impact on the math community that they're now being used by Desmos to anonymize names. Try to get yourself to slide 5 in the next like 5-ish minutes so we can all come back together. Now, here's the other trick that I want you guys to start to think about any time you find yourself thinking, what should I do with myself? As we get, hey, I got a lot of people talking at the same time as me. As we get into quarter 3, work doesn't really slow down until we get into quarter 4. When you find yourself with fragments of time, use them for something. So pull out that homework sheet and answer a couple problems while you wait for us to catch up to you at slide 5. What is the what keep changing? People might be changing their answers, their data points. So this person obviously looks like that might be an outlier, same kind of way down there, but we can see a relative trend go on. Yeah, it updates as people type into their tables. So if 5 people type into their table at the same time, you'll see 5 points. You are welcome. I should probably show that to the class too as it changes. It's interesting.
It works. It curves.
You're right. And you're right that it curves. I don't know about whatever else you said.
Oh wait, no. I just said the graph curves.
Oh, well, there you go. That's the same answer right there.
There we go. Yeah, that'd be more something.
It can just be a comma. It can be the thing that separates X and Y when we're doing the coordinate.
Oh my god.
Yeah, it could be a place value holder, right?
Or another thing, if you're in like Mexico or something, it could be the decimal point.
So the data that you see on slide 4 is changing as people enter values into their table. Now, do not allow this table to make you go back and change your data if you're confident in the data that you entered. Now, if you're iffy in the data that you entered, you might notice we have a few points here that don't necessarily look like they fit our trend, right?
Yeah.
And we would call those points outliers. So it looks like we might have a few. All right, because I know you've all been desperately waiting for more random card action.
Yay!
Avi, what are you noticing? Just give me anything. What are you noticing?
The graph looks pretty curved, not like flat.
The graph looks pretty curved, not like flat. I would agree with that. Yeah. Alex, what are you noticing?
You?
Yeah, you, Alex. Sorry, I always forget there's 2 Alexes in here.
Oh, wait.
And Dale's not here today.
most of them are like pretty in a section area, except for like a few, and somehow someone fit in a one diameter thing 50 different pennies. Somehow.
Apparently now somebody fit 60 in there too. So I think we have some people entering some silly data potentially, right? Some inaccurate data points here.
They're not outliers, they're liars.
So-
With the updating.
So again, I would encourage you to exhibit the mature 7th grade classroom behavior that we expect out of all of you. Some of you are not being very good data scientists right now. You are allowing your silliness to get in the way. Charlie, if we ignore those silly outlier points, and actually a few of those points could be right that are kind of closer, but the ones that are really far away, yeah, we can kind of guess that those aren't. And if I turn this screen off, I think some of you would be less silly, because it's like when you point a camera at somebody and they can't help but be stupid. But Charlie, if we ignore that stuff, what do you think this data's like showing us? Like, what's this mean? If we look at like Y, X, those things.
I believe it's showing us that with a larger diameter, we can fit a lot more pennies than the one that we had. So for example, say we have one diameter.
Yeah.
One diameter circle. We can fit like, let's say 8 in there.
Okay. And we'll say 1 is 1 whatever. We made up some unit. It's 1. We fit 8. Okay.
We fit 8 pennies. Then we go to 2. It fits, say, 20 pennies.
Ooh, why not 16?
Because I believe the line would be exponential. Because it's not proportional.
It's not proportional.
The space between the pennies goes up, so then you can fit more than just double the amount of pennies.
Yeah.
Alina, what are you thinking? I'm going random cards to try to get different thoughts. Charlie thinks it's exponential. You feeling like it's do you think it's linear, exponential, or quadratic? I guess we can go with.
Exponential because like you can see it's not entirely linear because there are points that like the pattern doesn't show all the way linear, and it's definitely not quadratic because it doesn't make a U shape.
So on slide 5 that I haven't shown you yet, take 2 to 3 minutes, type up your thoughts. So I know people want to share their thoughts. Do not take this as an opportunity to try to be silly stupid, right? None of us are stupid in here, but some of you like to kind of act sometimes like, oh, I want your true thoughts on what we're seeing because I want to be able to unanonymize and show people the feedback from our class. But earlier in the year, we had issues with people just trying to be silly and you're doing it for the reaction. And I don't want to unanonymize if we're doing it, right? So take 2 or 3 minutes, try to give a good justification of why you chose quadratic or exponential. I'm not quite sure, because quadratic, like we talked about before, the parabolas, they look like a U, and this could just be part of the U, or it might, or I don't know, it might be exponential.
No, but it can't because it can't be part of the U because it can't be when it gets smaller.
There's no negative.
That doesn't mean the relationship couldn't be described as quadratic. So remember, when we talk about functions, we then restrict domain and range, right? What inputs are we allowed to use? And that determines what outputs we'll get. Don't tell yourself it can't be quadratic because it can't U. It can still have a quadratic relationship. Just we'd only see like half the graph. Simon?
What's quadratic? A parabola?
It's when you modeled to try to like drag your points, and when you had like the click button, so you on your screen you have a click option here, right? When you click linear, it's going to force a line. When you click quadratic, it's going to force it to become a quadratic when you drag the points. And when you click exponential, it's going to force it to be exponential.
But what is a quadratic?
Well, you don't know yet.
Oh, so
Ooh, you could search it right now. So if I click quadratic here, it's going to force my function to become quadratic behavior. If I click exponential, it's going to do the same thing. It's going to force my graph to be exponential.
Quadratic, and I got websites selling cheap
Yeah, you need to type in quadratic equation or math quadratic or quadratic function. You need to give it a little bit more on the search. And I'll I'll unpaste you guys. Let's see what we said for number 5. So it has a slight curve, not a huge one. Sure, it could be quadratic, but on this I'm leaning towards exponential. Exponential is often described as a drastic increase, and that is how the line is moving. Scatterplot has a small curve in its pattern. The graph curves, if there is negative space, you cannot fit anything in it. I think a quadratic line works for this kind of graph because the line of best fit curves. Graph looks like it's a curve. Linear doesn't curve, of course, so we know it's not linear. So can we all agree it's not linear?
Yeah.
Okay, good. So we can see it's not linear. And actually, Patrick, I don't know if you're picking up on this yet, but this goes back to a conversation you and I went around with the area relationship when we talked about scale factors. Do you remember that conversation? I'm not going to put you on the spot. You remember what we were talking? This is that conversation. So you know how back then I said, like, we haven't quite learned this yet, we will? So Patrick was working on some homework at home, and his dad, your dad probably, I'm guessing? Dad, brother, somebody? Or did you just, like, think it up on your own? So he brought in this relationship that he had on his test. And essentially my answer to him was like, man, you're like a couple weeks ahead of us. We haven't seen this yet. But it was that test back where we were comparing the scale factor change that perimeter results in versus the scale factor change that area results in. Here what we're looking at is area.
So it would be r squared times 5.
Don't know.
R squared. Wouldn't that be a circle?
All right, keep going. You have more slides.
Oh, tight.
I think I know that.
Oh, my bad. You're going to need a calculator. But you have a computer, so I mean, inherently you have a calculator.
I like it better.
Same. I agree.
2.9. No.
You're okay. What'd you think?
I was related to picture.
Oh, would have totally messed up.
But it's me.
Are you calculating this, or are you just guessing what this comes out to? You know how to do 2 to the 22nd power? That's a really long, because that's 2 times 2 times 2 times 2, which is like 22 times.
Do I do the 2 or the 1.48?
You plug in your x first. So when
And then
x,
past that, do I do?
yeah, when you do the subtraction, then you square it first, and then you do the multiplication. Because exponents happen before multiplication.
How do I do
Multiply it by itself. So I'm not sure if that calculator has a nice square button. That's right there. But you're good. Now you've got to type in some more stuff. So there you go. There's that square. I'm really curious about who could get to extension 9 and give us a good response to that. So if you get through all the parts you're supposed to, 8 and 9 are extension questions. I'm very curious.
Is there another fun answer? Because my thing
Well, everyone has different equations.
yeah, but we're still
Why is it doing that? I got way more pennies than I think I should have got.
Let's say 5 minutes. We need to bring it back together and have another conversation. I'll give you 5 minutes to work. Hey Logan, we do this in the future. You gotta sign into your WS Cloud account, dude. Or you log into that account because you have old Desmo stuff from in the past. Did you log into your account for a specific reason, or did it just happen? Never mind. Next time we get on Desmos, make sure I get with you as we're logging in. I just want to make sure you're using your school account so all that stuff gets saved in there. Yes. Bear, I think you have 2 different computers that were goofed up on here, and then you actually got it to work. All right, Yeah, you're gonna have to spend $6,000 on pennies. Because we can divide that by 100, right? If we move that decimal 2 times over, that's gonna be $6,000 worth of pennies.
It's just how many pennies.
Well, yeah, for 22 in circle.
Would you put 22 in this exponent form?
Well, if it's an exponential function, yeah. Because remember, our x down here, we said our x is circle's diameter.
Oh, well, that's a lot of pennies.
Does that make sense?
No.
If your answer doesn't make sense, maybe we need to go back and adjust something.
No. Oh, yeah.
No?
I deleted all my progress.
Oh, I'm sorry.
I did not know.
Yes. Oh, will it not let you click back here?
No, I just
This is my first time working through this activity.
I don't know how to do this expression back.
So the number of pennies is your y, right? And that's why this is an extension problem. I haven't taught you how to do this. So this is a pretty difficult thing to try to solve. We don't know how to do that yet. You don't need to. That's why it's an extension. So, anyone really confident in their exponential? Like that, like I could share yours? No?
Well, you already shared my
Well, who are you?
Leon Hard.
Leonard Euler. I love using the anonymized people because then we can talk about like that. First off, we just don't know how to pronounce these words. But yeah, that's an old spelling of Leonard Euler, actually. Yes, so we can talk about that, but we don't have time. So at some point, you've got all that knowledge base, right? So if you want to know about some of these mathematicians, Logan is probably your person to go to. So this is what Leonard Euler has said is his exponential function. It matches pretty well, right? Like, can anyone say this is a terrible line of best fit? No, I mean, I think it's pretty good. So then the equation is given as this, right? 1.84 times 1.801 to the x, where x is your circle's diameter, and y is our number of pennies.
Oh, I think I wrote them.
Now, when we actually put our number of pennies in here and do the calculation, I'm skeptical this is not what we get. Because to do this calculation, we're going to do the exponent first. Right, so 1.801
I just took down the
to
number.
the 22nd power. Then times 1.84. That gets us, for a 22-inch circle,
For the record, look at his Y.
this is Alex's number of pennies for a 22-inch circle, which, if we want to envision a 22-inch circle,
That's what I put originally. It's just I took down the number because it didn't feel right.
probably about that. So Alex says he took down the number because it didn't feel right. Alex, why didn't it feel right?
Because, one, there's no way that there's 769,342 pennies in a 22-inch diameter circle.
According to Alex's math,
I think you might need to
which
say
now
something
he
here.
is kind of abandoning that math that he had thought was right, there will be 769,000 pennies in a circle of that size. It will only cost him $7,000 to penny that circle. Does that seem right? Probably not. Right?
Where's our
Now,
solid evidence that-
I'm not saying he did the math wrong. This is right according to the math. And actually, the computer generated Alex's equation. Right? Alex's equation was not generated by him. The computer created this. But now we're starting to feel like it might not be right. Anyone have a quadratic equation they're confident with? Or Ellie, your hand almost went up. Can I use you, Ellie? Henry, who are you? Who's your mathematician?
I am EO.
You're who?
This guy down here.
Oh, literally he. Oh, I don't know who that is. So, hold up. Check out Henry's line. Does Henry's line look like it fits a lot of our data? Yeah. Now, he chose quadratic. So when he went forward, this is his equation. Now, if we want to use this equation, x is still our number of pennies. So we follow our order of operations. We're going to type 22 into our parentheses first. So we'll do 22 plus the 0.03. We will square that value. We will multiply that by 1.33. And then we'll subtract 1.3. And Henry, in the same size circle, right? Same size circle. Henry gets a result of 644.
A little bit more believable.
A little bit more believable, right? So, if we just went back to just the data we had collected, could exponential or quadratic look like it would fit? Yeah, either of them looked right. What do we see when we start testing calculations? Well, quadratic seems more realistic, right?
And it's closer to the actual number.
Will we be able to calculate it just from the original diameter?
Give me your attention. That's why I paused you. What we're trying to get you to see here is exponential functions get out of control. And here's why. I need you to write down two things today. So either if you want to grab this sheet, and actually we're going to fill in a little bit on this sheet, so get this back out, please. But you might want to just grab your notes that we've been working on. Like, just grab out the last piece of graph paper you had. Today is 811. Guys, number one said get out the regular. Like, that means get out the regular, right? So we should have had out either the last notes we were working on or a new sheet of graph paper. This is why we had those tasks up there. Please don't ignore number one. Even though it stays the same, we need graph paper pretty much every day. So non-linear functions, sorry, I should probably say functions.
This is the title?
Just this little section, yeah, the two things I want you to write down for today are just both non-linear. Exponentials work in the form of a times b to the power of x. And as we get deeper into powers, we'll get real comfortable with saying that a power is representing, anybody? Repeated multiplication. So seriously, if that power is 5, it means multiply b 5 times. So b times b times b times b times b times b times, I don't know how many that was. But a lot, right? So if x in this situation becomes 22, we're multiplying whatever that number was. 20, not times 22, but 22 times. So that 1.83, forget whose base value that we did 1.83 times 1.83, 22 times. Versus a quadratic, we'll write in white since I know you guys like that. A quadratic relationship is y equals a times x squared, the power is always 2, plus b times the same x plus c. So in a quadratic, although it still does provide that curve that we're looking for, it doesn't increase like crazy, right? This, every time x steps up by 1, we multiply again by b. Here, when x goes up by 1, it just changes the base value that's getting squared. So if you want to take a moment, just go to desmos.com. Like, not student.desmos.com. Go to desmos.com. Just desmos.com. You can if you want.
Keo is from South Korea. I can get much farther than that.
If you hit start graphing, we're going to just play for a minute.
Yay.
Type in y equals, I don't know, like 1 times, which we can use the Alt 8, or I don't know how it works on a Chromebook. If you click this little button down here, it will pop up your functions. If, the little keyboard button, if you want to quickly get to a power, hit Shift. I gotta check Chromebook that it works the same. Shift 6, that up arrow, will change your function into writing a power.
You can just click the A, B, and then.
Oh yeah, this button does the same thing. You can either click the
Shift
times
8.
button down here or Shift 8. Shift 8 with the asterisk means multiplication. So we could compare that to y equals, I don't know, we could just say like 2x squared. Doesn't really matter what our other values are. We can just make them all 2's just for fun. As we zoom out and look at this graph behavior, see how red crosses blue? And then red keeps getting steeper, 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 and blue keeps going out. Now, if you want to see a lot more of a dramatic difference, if we change that A value to something more similar to what we were just talking about, right? Wherever, who were we looking at? Quadratic. So here our A value is like 1.33. Right, actually, I could copy this quadratic. Whoever is Fan Chung, I'm grabbing your quadratic and bringing it over here.
Hopefully you're right.
So here's Fan Chung's quadratic, right? Versus if I get somebody's exponential. Sorry. Annie easily. Here's your exponential. Let's just compare these two functions that both look like they could model our pennies. So look, this is what you could see on your graph. But then as we go out here, things get a little crazy with that purple line. It gets real steep.
So I almost got it right by just guessing.
Now, here is the hack then. If you wanted to figure out your x of 22, you can just type in x equals 22 and find where that intersection is. So there we go. It gives me the intersection point. So for that green function, this quadratic, it intersects x equals 22 at 643. So this was a different function, right? Somebody else's quadratic. We will pick up our work with nonlinear functions tomorrow. Please put your Chromebooks away wherever you got them, Alina. Because it squares it. What's -2 squared? It's not realistic. We have to restrict the domain. So we would then say our domain has to be positive x values. Does that make sense? We then give it a restriction. We like give it a rule. And we'll talk about that tomorrow. The situations that don't make sense, we'll make them make sense. What's up, Henry?